Right, thank you. Thank you to the organisers for having me present here. Just want to confirm again, everyone can see and everyone can hear? Good, okay.
Yes.
So, yeah, this work has something to do with optimization, but it doesn't have much to do with metric bounds or transversality. So I hope that the audience today still gets something out of it. I hope it'll be interesting for you. Sorry, let me just, okay. So this is joint work with 3 collaborators, Dabin, Fatma, and Simge. They're all, well, I did my PhD with Dabin, and Fatma was my advisor at Carnegie Mellon, and Simge is at Northwestern. And I want to begin by motivating what I'm going to talk about with an example. Let me just hide this actually. Ooh. Okay, so this is the example I want to start with. It's a transportation problem, right? The problem is to transport quantities of a certain item from a set of factories. The factories are the squares on the left to some distribution centers. So this is a classical transportation problem from operations research. We have some numbers. M1 and M2 are the production capacities of the factories on the left, and the Psi1 to Psi4s are the demand for each distribution center. So when you transport the quantities, you can only produce a certain amount from the first factory, and you want to send enough quantity from both of the factories to satisfy the demands from the for the distribution centers, for instance. And of course, delivering 1 unit from one factory to one distribution center incurs some marginal cost, right? And so this is the formulation. It's just a linear program. Here we have the production constraints, and we're trying to minimize the total cost of transporting all our units. But here we have something called a chance constraint. So this says that the probability that we satisfy all the demands at every distribution center has to be at least 1 minus epsilon. So if epsilon is 0.5, then that means we want at least a 95% chance of satisfying all the demands. And the reason why we have a chance constraint is because the demands are, in practice, they fluctuate. So we treat them as random, right? So this is an example of a chance constraint. This is the general form of a chance constraint. Our decision variables are X. We're trying to minimize some cost function. It doesn't have to be linear, but without loss of generality, we can take it to be linear. And we need to choose our decision variables from some domain, script X. And the key thing is that we have this probabilistic constraint here. You know, if psi was not random, then we would just have this constraint fx psi greater than or equal to 0. But psi is a random variable. So for a fixed x, fx psi is itself a random variable. And we want to say that with high probability, we're going to satisfy our constraint of interest, right? And the form of the f constraint function, we're going to look at piecewise linear form, right? So that's this here. And the only restriction we make is that, well, we look at, you know, bilinear functions and then we take a minimum over them. But the bilinear terms here, the coefficient matrix for this bilinear term in X and the random vector Psi, they need to be constant across all the different P's. So we're not looking at a completely general form, but it is fairly general enough to cover a lot of applications. So how do we solve this chance constraint problem? The typical approach is sample average approximation. So we have our true distribution P star from which psi is distributed, right? But what we're going to do actually is draw some IID samples, psi I from 1 to capital N. So, and then we treat this as our data. And then we're going to use our data to approximate this probability of satisfying the constraints. So we approximate it with the empirical probability on our data set, right? It has different names in ML and stats, but in optimization, we call it sample average approximation. So why can't we handle this guy on the left directly? It turns out we can, but we have to make, certain very restrictive assumptions. Like if psi is a normally distributed random vector and this f function is just one single linear term, then we can write out something. But apart from that, there's not much we can do. And in practice, this p star is often unknown, right? And even when it's known, evaluating it is difficult. So that's why we look at sample average approximation. So this is the sample average approximation. It looks very similar to the chance constraint program I had before, but I replaced the chance constraint with this empirical approximation of the chance constraint, right? And so when I do this, it turns out that under some assumptions like the piecewise linear assumptions for f, this is mixed integer representable. So we can write a mixed integer program for this and plug it into our favorite software like Gurobi, right? And the interpretation is that we need to satisfy this constraint fx psi I greater than or equal to 0 for at least n times 1 minus epsilon samples, right? So that's the sample average approximation. But the complaint about using this thing is that the outer sample performance is often poor, particularly for small or medium sample sizes, capital N. So what that means is that if you solve this SAA problem and you get some solution X, well, you will be guaranteed to satisfy this constraint, the empirical constraint, but that does not mean you will satisfy the true chance constraint, right? So the outer sample performance is poor, and people have observed empirically that it's sometimes it can be quite, this thing is quite far from being satisfied, the true chance constraint. So one way to get around this is to look at distributionally robust chance constraint, right? So the idea is that if you look at your empirical distribution, right, then with high probability, this empirical distribution will be close in some sense to the true distribution, right? And there are more precise results here, these concentration bounds that say that, they will be close within a certain metric D, and they give, they quantify what close means in terms of the sample sizes and things like that. But the intuition is that, with high probability, this empirical distribution will be close. So what we're going to do is, instead of saying we only want to satisfy this constraint for the one empirical distribution, we're going to try and satisfy this probabilistic constraint for all distributions in some radius theta ball around the empirical distribution. And so with high probability, well, this is my ball around the empirical distribution in the space of distributions, right? So with high probability, there's a result that says the true distribution will be inside this ball. So that means that if we impose this distributionally robust chance constraint, then that means with high probability, our true chance constraint will also be satisfied. So we will have at least probability 1 minus epsilon that this constraint is satisfied under the true distribution P star, right? And so that's the strategy. And intuitively, again, if n is large, then we have more confidence that Pn will be close to P star, so we can make the radius smaller. And when n is small, we're not as confident, so we make the radius larger. Right? So now the question is, what metric are we going to use? And our work looks at Wasserstein, the Wasserstein metric between distributions. And the reason for this is that it's become popular in optimization and machine learning. I'm not quite sure why it's become popular in machine learning because it's not my area, but in optimization, the reason is because the Wasserstein, when you compute this worst case probability inside the Wasserstein ball, we can see that the support of the worst case probability is different to the support of the empirical probability. But this is not the case for other types of distances between probability distributions. If you formulate your ball differently, for instance, with a KL divergence, that's not going to be the case. We just see that it has the same support as the empirical distribution, but the weights, instead of 1 on n weights, the weights are kind of tweaked a little bit. So that's why it's become popular in optimization and machine learning, and that's why we're going to look at it. Okay, so now that's what we're going to look at. We're going to look at a Wasserstein ball around the empirical distribution, but we need to reformulate this kind of worst case constraint. So the constraint says that for any distribution P inside our Wasserstein ball of radius theta, this chance constraint needs to be satisfied. So how do we reformulate that? We're going to do that through defining something called the distance to violation. So for a given vector psi and a decision vector x, this distance to violation is just a number which tells you how much you have to perturb psi by in order to violate this f constraint here. All right. And so the result in the literature says that for Wasserstein ambiguity, this worst case constraint is actually equivalent to a certain risk measure or the conditional value at risk on the empirical distribution at a certain quantile, being larger than a certain threshold given by the radius and the epsilon, right? And so the conditional value at risk basically means that you take the lowest epsilon times n distances amongst all these numbers. So it's just the same distance to violation, except you're plugging in the data points xi now for a fixed x, right? So you take the lowest epsilon on n of those distances, and then take their average. And then using the standard Rockefeller characterization for the CVAR, you can write this CVAR term as the maximum of, well, you can write it as the result of an optimization, a maximization with auxiliary variables T and Ri. And that, when you plug that into this constraint here, that allows you to lift things into, well, you can lift into more variables T and Ri. So that's exactly what we do here. We had the distributionally robust constraint, but we used the CVAR formulation. And then this is the lifted representation. And the last step is to reformulate this distance constraint. So now this distance obviously depends on how we define our function f, right? And so for the rest of this presentation, I'm just going to consider a very simple definition for f, which is just a linear function of x, right? And we just have an additive term for xi. So xi is a one-dimensional variable here. And so the distance to violation is just a maximum of f and 0. And what that means is that if fx psi is already less than 0, then we don't need to perturb psi at all. But if it's greater than 0, then we need to perturb it by, well, that much, all right? But as I said before, our results do extend to different constraint function forms, right? More generally, these piecewise bilinear functions, with the only condition being that this bilinear term has the same coefficient matrix A for all the different pieces. Okay, so now this is the constraint involving the distance, and we can see that it's a disjunctive constraint. So it says that either t minus ri is less than 0 or t minus ri is less than f x psi I, right? And we can model this with a binary variable. This is a standard technique, big M, using big M constants and binary variables. That's how we model the disjunction there. And our big M constants need to be sufficiently large. There's a certain condition here, which we want to look to improve actually for the big M constants. But if you do it naively, there's a certain condition that we can kind of use to compute the big M's. So this is the MIP formulation, right? But the problem is that it's difficult to solve, even for small n equals 100, so very small n, right? And especially for small radius theta. So our contribution is to make this scalable up to, well, 10-fold to 30-fold. So we go from n equals 100 to being able to solve, or approximately solve problems n equals 1,000 to 3,000. Okay, and so how do we do that? The way we do that is to find a link between SAA and this distributionally robust chance constraint. And it leads to a number of enhancements, which I'll go through now. Right, so the first thing is I need to describe what the link is. So this is the feasible set for the SAA, right? And we have a MIP formulation for that in terms of our data, psi. And then this is the feasible set for our distribution robust chance constraint, depending on the data as well. And so the observation is that in general, obviously we will have that because if you set the radius to 0, the ambiguity set only contains the empirical distribution. So we increase the radius, we enlarge the ambiguity set, but that means that the distribution robust set is contained inside the SAA set. So naively, we can take these blue constraints and add them to the red constraints, and those are valid inequalities, but they require different binary variables. So you can't, just add these constraints naively to the red constraints. You need to replicate the binary variables. That's the naive way. But then if we think about it a little more, the key result number one is that we can use the same binary variables. So we just took the blue constraints and added them in with the same binary variables Z, right? And what this leads to is that now we can exploit the structure from previous studies on the SAA constraints, right? So this is a structure that pops up in the SAA constraints. And then the nice thing is that, there's something called the mixing procedure, which allows us to drastically reduce the big M constants, right? So instead of having a capital M, we can reduce them to some little m. I'm not going to go through this procedure now, but that's what we can do. So now we can do this. We can take those results for the SAA substructure, and now we can try and reduce some of the big M constants in our DRO structure. So we have for each data point, I, right? We have these 3 inequalities now. And then we can check that these 3 inequalities, the first 2 come from the DRO constraints. The second one is just from the improved SAA constraints. And this implies that this second DRO constraint with the big M, capital MI here, you can replace that with a little mi here, right? So we can reduce the big M constants, right? And these will replace the big M constants in our formulation. So that's good. Another, how am I going for time? Okay. Another result is that we can think about this C bar formulation here. And it's a standard result that, well, this is an optimization problem over T and R to compute this C bar, right? And it's a standard result that the optimal solution for T will be the epsilon times n plus 1 smallest value amongst these distances, which are these guys, right? And then what we can see is that actually the ordering of these distances just depends on the ordering of the psi i's, right? So we can let Q be the epsilon times n plus 1 smallest value amongst the psi i's, right? And so what that says is that if we have our psi i's greater than or equal to Q, then immediately we have our T is less than or equal to this distance, distance to violation, psi, in terms of psi I and X, right? And so this is the constraint that pops up in this C-var representation, right? But if we rearrange, well, we have Ri's and then this distance minus T on the right-hand side. But from here, this distance minus T is non-negative and Ri are non-negative just from the representation of the C-var. So what this means is that this constraint is vacuous, so we can actually remove them. So in summary, we can improve these big M constants here, right, for the distributionally robust formulation. And we can remove some constraints here, right? And the final thing we can do is look at valid inequalities. I'm not going to go into too much detail here, but basically what this means is that we look at certain substructures and they involve binary variables. So you can ask, what is the convex hull of these substructures? So can we write this? Can we relax these variables to continuous, but add in more inequalities to get their convex hull? And then the question is, what are these inequalities? Well, for the substructure arising from the SAA constraints, it's been shown from previous work that the right inequalities are mixing inequalities. And then the substructure that we look at for the constraints arising from the DRO formulation, well, it turns out we found a connection between robust 0-1 programming and that substructure. So we also have some inequalities which describe the convex hull of this substructure. So what this means is that we have these two classes of inequalities that we can implement into a branch and cut type framework. Okay, so that's our work. I want to discuss briefly some computational experiments and then I'll be done. So the computational experiments look at a transportation problem with a chance constraint here, distributionally robust chance constraint. And we generated them in some way, which I won't get into details here. But what we're going to compare is the basic formulation versus our improved formulation, where we reduced the big M constants and removed some of the vacuous constraints. And we also compared that with our improved formulation, where we also separate those valid inequalities, right? And we look at the time it takes to solve, if it solves within 1 hour, or if not, then we look at the gap at the end of the 1 hour. So these are our results. We generated, we generated 10 instances of 100 data points each, right? And what we saw was that this is the basic formulation, which was in the literature already. So for the smallest radius, so these radii are ordered from smallest to largest. So for the smallest radius, theta 1, what this says is that the basic formulation was able to find 10 feasible solutions for that problem, but was not able to solve any of those instances to optimality. So they had an average gap at the end of 1.16%. This is reported by CFlex. On the other hand, our improved formulation solves all 10 instances in an average time of 4.29 seconds for that smallest radius. And for the formulation with separating valid inequalities, we solve it in a slightly higher time, which again makes sense because it takes some time to separate those inequalities. So for n equals 3000, we see a more striking difference here in that, for the smallest radius, we see that the basic formulation is not able to even find any solutions, feasible solutions after 1 hour. But our formulations are able to find solutions for all 10 instances. And the average gap is 0.78% and 0.48% after 1 hour. So that's a nice improvement. And in general, we are able to get an improvement across the board for all radius values and different sample size values. Okay, so that's all I have to say. I guess I'll finish by saying thank you for your attention. If you have any questions, I'm happy to take them maybe offline, or if I have time now, then I'll answer some questions. But also, if you're interested, here are the links to our papers. Yeah, thank you.
Okay, thank you very much. And any questions? Yeah, I have a short question. So, do you have this theoretical convergence results within your algorithm? Or?
Yeah, well, I mean, if you're talking about the theoretical convergence of the distributionally robust framework in general, that was.
Yeah, I know there are some, but I mean, if you use this big M and then you reduce this big M using another technique, then I mean, the actual algorithm you are using.
Oh, well, no, we do prove that reduced big M value is valid. So it's a correct formulation.
Okay.
Yeah. So that, if you solve that, then you will, get the right solution. Yeah.
Okay. Yeah, good. Yeah. Any other questions then? Okay, if there's no any other questions, let's thank the speaker.